Hello everybody. Welcome to today's webinar. Really appreciate you taking the time to join us, and hope that you find it interesting and informative. So I'm Jamie Clayton. I'm Operations Director at Freeman Technology, which is part of the Micromeritics family, and I'll be moderating today's session. Before we get started, just some quick guidance on the format for the event. So you'll have noticed that all attendees are in mute mode or listen only mode. If you do have any questions, you can click on the speech bubble or question mark icon in the GoToWebinar dashboard, and you can submit a question there. Just so you're aware, questions will only be visible to the organisers. And at the end of the presentation, we'll have time to address a few questions, time allowing. But if you do ask a question, please be assured that one of our team will come back to you in the coming days to follow up on that and provide you with any further information. And also a recording of today's event will be made available afterwards for you to watch on demand. So as you may be aware, we've been running a series of webinars over recent weeks. If you've already joined some of these events, then thank you. Hope you found them useful, and we look forward to welcoming you to future sessions as well. And amongst those future presentations, we have some great guest speakers planned, so keep an eye on your inbox for information about those. But today we're fortunate to be joined by the first of those, Enrico Gallino from Ricoh UK Products Limited. So Enrico is a materials engineer at Ricoh, and today he's presenting on characterization tools for evaluating polymer powders for laser sintering. As I say, he's a materials engineer at Ricoh, having worked there for over 2.5 years. He has a master's and a PhD in material science related subjects, but with a main focus on polymers. And prior to working with Ricoh, he gained experience in powder handling applications across multiple sectors, including academia, energy, cosmetics, and steel. So on that, I will hand over to Ricoh, who will tell you a little bit more about Ricoh themselves, and also their work with polymer powders. So please bear with me while I just transfer to Enrico.
Thank you very much, Jamie, for the kind introduction and for inviting me to present at today's webinar. Hi, everyone, and thank you for joining the webinar. The purpose of my presentation today is to provide you with an overview of some of our additive manufacturing activities at Ricoh, but most importantly, some of the characterization tool we can use to evaluate powders for the selective laser sintering process, and how this tool can be used to qualify new materials, define if they are suitable for the selective laser sintering process, but that can also be useful for quality control purposes to have a robust operation in place. So to start with, and for those of you who were not very familiar with Ricoh, we are a large Japanese company with headquarters in Tokyo. We have a global presence as we operate in more than 200 countries, and we have nearly 100,000 employees. The company was founded in 1936, originally to manufacture and sell sensitized paper. But since its foundation, the company has very much evolved. And today our mission is to help businesses transform their process to become more efficient, productive, and profitable by empowering their digital workplaces and digital operation. Innovation and quality are at the heart of what we do. And as you can see, we hold more than 50,000 patents worldwide, and our operation comply with several quality standards. And we are also very much driven and committed to providing a standard of excellence that drives sustainability and improves people's life. In terms of product and services, most of people know Ricoh for our office printer. However, our product portfolio and capabilities are larger than that, are much broader than that. We do have a wide range of commercial and industrial printers, as well as inkjet heads. But as you can see on this slide, our portfolio goes beyond printing, as we also produce and commercialize vision system, cameras, semiconductors, solar cells, and we have recently developed a bioprinting solution, and we also offer a wide range of other office solutions, such as interactive whiteboard, video conferencing system, document and data management solution, and of course, last but not least, 3D printing, which sits in our industrial printing line of business. And also, just to give you a little bit of background, initially Ricoh entered the 3D printing market by supplying printing heads to 3D printer manufacturers, but also by using the technology within our group on our own product and manufacturing operation. Then we have launched our selective laser sintering printer in 2015. But since last year, we have very much refocused our strategy, at least in Europe, on the offering of a range of additive manufacturing service. So our additive manufacturing operation in Europe are based in Telford, which is right in the middle of the UK, about 40-minute drive northwest of Birmingham, where we have a 600 square meters facility that we have expanded last year, nearly more than doubling the capacity with 1.3 million pounds investment. In terms of printing technologies, our focus is primarily on polymers, and we do offer mainly powder-based technologies such as selective laser sintering and multi-jet fusion, although we do also have capability for FDM printing. But as we want to provide our customer with a truly end-to-end manufacturing service, in addition to the printing part service, we also offer a range of complementary service, including post-processing, design, as well as some more R&D oriented activities such as material characterization and material development service. And everything we do is also underpinned by several ISO quality standards. And for your information, we do also have a similar facility in Japan to serve the local market over there and in Eastern Asia. As I said, we do offer an end-to-end range of additive manufacturing services to help companies fully unlock the potential of the technology, not only for prototyping, but and especially for serial production, as we firmly believe that additive manufacturing is a capable and an additional manufacturing tool sitting alongside traditional manufacturing technology for serial production. In this way, we believe we can help our customer to transform their processes and operation and become more agile, profitable, and sustainable. And innovation is really one of the key driver, as we are also keen to invest in the latest printing technology, but also develop bespoke solution for our customers. And when it comes to innovation, this is also true for materials, as these are definitely one of the pillars and enabler of our strategy. However, if you look at the material choice available for traditional manufacturing process, you have a very broad range of material available, whereas for additive manufacturing and more specifically for powder bed fusion materials, the material choice is still limited, and the market is still very much dominated by polyamide-based materials such as PA12 or PA11 or composite of this material, which accounts for something around 90% of the market. So in order to develop new applications and help our customer to develop use case for using additive manufacturing for serial production, there is definitely a need to develop more materials, and especially materials that could be easily and consistently being processed in the printers. In our case, obviously, we don't do that on our own because we are not a material manufacturer ourselves. So we need to work really closely with material manufacturers and end user to source and develop new material to enable those new those new applications. And we do that sometimes really starting from the early stages of the development. And in order to do that, we need to have a good understanding of what the material properties are and how the material will possibly behave in the process, in order to be able to also have a dialogue with those partners and together refine the material properties to be able to develop those material, and that those material are suitable for the end process. Also, once you have validated your materials for your process from a quality perspective, and if you really want to use additive manufacturing for serial production, it is very important to define a powder specification and check it before every build that your powder meets the required criteria in order to have traceability of your feedstock, and also some robust operation in place. And to do all these things, it's really important to try to answer those questions. What makes a good powder, and what properties are needed? Because you cannot just take any powder, put it into the printer, push the start button, and off you go. You will get your parts. It's a lot more complex than that. And to be honest, to clearly answer those questions is still quite a challenge at the moment, because there are not clear standard defined and really specific to additive manufacturing, and there are also clear gaps that have been identified for things such how do we measure in a relevant and standardized way properties such as powder spreadability, for example. And although there is a lot of work being done at the moment by organizations such as ASTM or ISO to fill those gaps, this is still very much work in progress. So if we look more in details at the correlation between powder feedstock properties, process parameter, and how those interactions influence the properties of the printed components, we can see that we are in front of a quite complex challenge. From a powder feedstock perspective, powders can be defined by a series of different properties, such as their thermal, physical, and chemical properties. And from a process perspective, we have on one side the lasers parameter. We can modify the printer, such as the laser power, the scanning speed, and the scan spacing, for example. And on the other end, we got other parameters that could vary depending on the model and the manufacturer of the printer. For example, the way the powder is dosed. This could be done by gravity from the top, fed from the bottom by means of a piston, or through a moving hopper. Or if you look at the recoater size and shape, Some printers have a roller-shaped recoater, whereas in other machine, this could be a blade or a knife, for example. And both the powder properties and the machine parameters and the way this will interact will influence the properties of the final part. And ultimately, what we want is to be able to produce parts with good mechanical properties in line with the material specification, parts that have low porosity. We want to minimize the defects on those parts, so we want to have a good surface quality to limit the post-processing step as much as we can, and all these things we want those things happen in a consistent way and across the full size of the build volume of our machine. So when we look at the actual selective laser sintering process and how the powder is handled during the process, there are actually 4 things that our powder needs to be able to do. The first one is we need to be sure that the powder is stable during storage, either before the powder is loaded into the machine, but also during the process, because sometimes the printing process could take a few days, in some cases up to a week from start to finish. And we want to make sure that the powder is not prone to segregation, consolidation, or degradation during this period of time. Then we need to dose the powder in front of the recoater, and we need to be sure that this is done in a consistent way in terms of the amount of powder we dose and the particle size distribution for every layer we want to put onto the powder bed. And also here, the powder will transition from static condition to dynamic condition. Once we have dosed the powder, we're gonna need to spread the powder across the bed, and we will need to have an even layer of powder across the bed and try to minimize the presence of defects, holes, and these kind of things. And we need to do this for thousands of layers. And here also is where the powder flowability and the powder properties, such as the powder shape, will start to become very important. And ultimately, once we have created an even layer of powder, we will need to melt the powder in specific regions to create our parts. And this is where other properties of our powder, such as the thermal properties or the rheology, will start playing a role. And again, we'll need to do that layer after layer, and we want it to be consistent. And at the end of the process, we will need to understand to what extent the powder properties have been affected during the process. And ideally, we really want to have a powder as stable as possible so we can recycle it and reuse it in the process. And we also want to understand when the powder is not good enough for the process and it's time to dispose of it. So if your powder is not perfectly adapted and suitable for the process, it is very likely that this can be the cause of issues in the process. Like, for example, here you can see that sometimes you can have a powder bed that is not very smooth or have defects in it, which can lead to parts with poor mechanical properties or poor surface quality, like in these two cases, or in the worst case scenario, even build crashes. And if the thermal properties of the material are not good enough, you will end up with parts with geometrical defects, like the one you can see here, and geometrical defects like curling, for example. And obviously, ending up with this kind of issues is very costly if we take into account that in some cases, material represent up to a third of the cost of the part. So how do we evaluate the powder properties and what tools we use to measure the relevant powder properties? In our case, we tend to look at the powders on 4 different levels. We can have a look at the thermal properties, such as the melting and crystallization temperature, as well as the material degradation as a function of the temperature. We can have a look at the rheology of the melt, which is important for understanding and predict part consolidation. Then we will have a look at individual particle properties, such as their morphology and the particle size distribution. And then we will have a look at how these particles will behave as an assembly, as a bulk. And so we will have a look at things like powder flowability, bulk density, powder stability, packing density. So if we start looking at the thermal properties required for semi-crystalline polymers usually used in the SLS process, this implies that the crystallization should be inhibited during processing as long as possible, and at least for a few sintered layers. So the processing temperature must be precisely controlled in between melting and crystallization of the given polymer. And this meta-stable region of what we can call an undercooled polymer melt between the melting and crystallization point of the material is called the sintering window. And we can evaluate those kind of property using dynamic scanning calorimetry, DSC, for example. And for our material, what we want is we want that this sintering window to be as large as possible. Because if, for example, the sintering window is too small and our processing temperature is too close to crystallization, it is very likely that parts will curl due to premature crystallization, and we will end up with a distorted part at the end of the process. If, on the other hand, the processing temperature is too close to melting, this will lead to a loss of definition of part features, because the powder particles close to the laser trace will stick on the molten surfaces and will prevent the formation of the part topography with the required resolution. But what is also important is to have an appreciation of the degradation temperature of the material beyond the melting, as this can have a detrimental effect on part properties and the recyclability of the powders. And for that, we can use TGA, the thermogravimetrical analysis, and evaluate what we call the stable sintering region of the material, which is defined as the temperature difference between the end of the material's melting peak and the temperature at which 1% of the material has degraded. And again, we want that this stable sintering region be as large as possible as well, like for the sintering window. However, from a practical perspective, when it comes down to define the sintering window, for example, we can have materials with a clear and defining melting and crystallization peak, but sometimes, like on the material you can see here, we also end up with DSC spectra where those peak, in particular the melting peak, are not clearly defined, so it becomes much more difficult to define the sintering window. And also with the fact that the melting peak is so broad, it is also uncertain whether entering the broad melting peak give rise to thickness issues for the powder. And on top of that, DSC spectra are just an idealized representation of thermal reality, as they are acquired using fixed heating and cooling rates, which are never being applied during the SLS process, as in reality we do have in the process undefined and hardly controllable temperature change rates, but at least we have here a starting point to evaluate the thermal properties, and also we keep learning by evaluating new materials. Then we can look at evaluating the viscosity of the melt, which gives some additional indication on the degradation of the material and possible issues with part consolidation, as a material with too high melt viscosity will not consolidate well, whereas if the viscosity is too low, this might lead to polymer bleeding into the surrounding bed, resulting in a poor part finish. And we can measure the melt flow index of the material, which is defined as the amount of material extruded through an orifice of standard dimension under a very defined and standardized temperature and pressure condition. And as the MFI is inversely proportional to the viscosity, the higher the MFI, the lower is the viscosity of the melt. And as you can see by the comparison of these two materials, the change in melt viscosity as a function of the build cycles might different from one material to another, as some materials, like material 1 in this case, will be more stable, whereas some other materials will tend to experience chemical degradation when exposed to high temperature, which will cause, for example, oxidation or increase in their molecular weight. And these changes can lead in the end to poor part quality. And so it is very important to track those changes to assess the recyclability level of a material, and also understand when the material will no longer be usable for printing. If then we start looking at the different method of production for polymer powders and the different particle size and morphologies produced by these different manufacturing methods, we can see from those SEM images that powders come in different size and shape. We can have powder with perfectly rounded and spherical shape, like this polypropylene material, which is actually the Ricoh polypropylene material. Powders with a potato shaped or a cauliflower like shape that are generally made by production method like precipitation or polymerization. And on the other hand, we have powders with more irregular particle shape, generally made by cryogenic grinding. And we do also have composite powders like these P6 powders with glass beads, where the polymer material is composed of irregular shaped particles, and the filler, the glass bead, are characterized by a round shape particles. Obviously, each production method has its own advantages and drawbacks. Polymerization, precipitation, melt bending generally produce particle with a more regular shape and narrow particle size distribution, but generally this comes with a higher cost, as those methods are much more complex and require special equipment and more skilled people to be implemented. Also, these are not really applicable to all type of materials, such as materials that are very resistant to solvent or that require the use of, say, nasty solvent to be solubilized. And on the other end, cryogenic milling is a more cost-effective technology and probably the most common method at the moment to produce powder for selective laser sintering. But as mentioned before, this manufacturing technology produces powder with irregular shape and a wider particle size distribution compared to other manufacturing methods. Obviously, if you have a look in the literature or in the patent landscape, new production methods for SLS powders are being developed. So we should expect in the future to see powders being developed with different morphology and particle size distribution. So it is really important to understand how the powder shape and particle size correlates with the bulk properties of the material. So if we now compare in more detail the particle size distribution of this material, we can quantify the actual differences in terms of particle size distribution and confirm that materials produced by cryogenic milling have generally a broader particle size distribution and contains much bigger particles compared to the powder produced with other methods. And this can also have an influence on the way we process these materials, as the layer thickness that we will use will be generally slightly higher, and this can lead to parts with a higher surface roughness. If we then can start looking at how these different powders flow by using a simple test, such as the angle of repose, say simple test because this is a quite easy test to put in place and is quite inexpensive. However, if you look at the results, the angle of repose of the powder are not too different, even though the polypropylene powder has got the lower value of angular repose. And if you remember well, this powder is the one that have this these particles with a nice and a smooth spherical shape. So in order to try to highlight more differences between those powders, we have invested in an FT4 powder rheometer, as these instruments provide a wide range of test methodology that enable to test both static and dynamic properties of the powder and generates a set of metrics to quantify the powder properties. The instrument also doesn't require a large amount of powder, so it's perfect for both quality control and R&D purposes, where sometimes the quantity of material available is limited, and also the testing methodology are not influenced by the operator or the way the sample is stored or handled, because before each measurement the instrument runs a conditioning step to the powder. And for us at Ricoh, there is an additional benefit because this instrument has also been useful for our toner operation to evaluate the properties of some of the toner powder we handle on our sites. And by using this instrument, we have found that the dynamic flow test is quite an useful and powerful one, because it enables us to differentiate the powder properties. In this test, what is basically happening is that we've got the rotating blade of the instrument moving downwards and then upwards in the vessel, which contains the powder, and will expose the powder to shear forces. and the normal forces and the torque required to perform this action are recorded. So we first run a set of tests at a constant speed. So this is the kind of the stability test. And then we run 3 additional tests to evaluate the variable flow rate, and we run those tests by reducing the rotational speed for each of the blade for each test. And in general, what we measure is the total energy required to move the powder. So from the curves obtained, it is possible to generate several powder quality metrics, and the results obtained show good repeatability, as indicated by the low standard deviation across the dataset. The stability index, which is this parameter, is close to 1 for the powders, and this is a good indication that all the powders appears to be stable to repeating test and to movement. Then if we look at the basic flowability energy values, we can see that the polypropylene powder here, which is composed of perfectly shaped and smooth particles, has got the lowest BFE values, meaning that this powder has got the best flowability among those powder. The value of specific energy are also quite low, meaning that the interlocking forces between particles are also lower in the case of this powder. The other powders with narrow particle size distribution and regular particle shape, like the two PA12, demonstrate also good flowability, whereas as expected, the powder produced by using cryogenic milling with more irregular shape have got lower flowability. So in comparison to the results obtained with the angle of repose, we are able here to really differentiate the flowability properties of the powder and gather a lot more information about the powder properties. It is also worth mentioning that we can actually process all this powder on an SLS machine and print actual parts, but these results are in good agreement with what we observe from a practical point of view, where powder with a more regular shape are easier to process on the machine. So let's consider now a set of powders all produced by cryogenic milling and having sort of very similar particle size distribution and particle shape. And the question we can ask now is, are we still able to differentiate those powder using the FT4 powder rheometer? And as you can see from the results, the answer is yes, and we can see that the powders have a very different behavior and level of stability, despite being all very similar in terms of morphology and particle size distribution. And then we can actually see that powder 6 and 7 have the best flowability. This might be related to a different amount or to the type of flowing agent it's included in the formulation, because this kind of additive are generally added to improve the powder flowability. Possibly the surface roughness or the porosity might also have an influence on these results. And we really probably need to investigate more the correlation between the powder properties and those results. As mentioned before, it is also important considering the effect and role of powder aging on the powder properties. So here we have considered two powders and compared the particle size distribution and flowability of the virgin powder and a powder after one printing cycle. And from a particle size distribution perspective, those powder are quite similar, both in the virgin and in the recycled state. The main difference we can see is that powder B contains a slightly larger particles after recycling. But if we now look at the results obtained with the powder rheometer, we can clearly see that powder flowability is affected by the aging, although the two materials are affected in different way. Powder A here in blue shows an increase in flowability, whereas for the powder B in red, the flowability seems to be decreasing. And at the moment, we have not been able really to fully understand what is causing those differences. The good news is that both powder are still stable after being recycled, and when we mix them, we have properties that are in between the virgin and the pure recycled powder. So to summarize the key message for the presentation, being able to characterize powder properties for the selective laser sintering processes is essential to support the development of new materials and their qualification. And you can also use those results and those tests to define some specification and the acceptance criteria to validate our powder supplier and guarantee that we can minimize build failures and that we can have a robust process in place. It's really important to use a multi-technique approach to understand the differences between powders at different levels and try to correlate this with the performances in the process. Because additive manufacturing is still a fairly new technology, and the technique used to characterize powder and the understanding of their behaviors are still developing. So for us, it's really important to keep learning from both our own experience with new materials as well, and also using the knowledge, the information that are available in the industry, in the literature, sorry, and I think it's also important as an industry to share those knowledge to make further progress in this field. And for me, another point that it's really important to highlight is that it is really important to evaluate the effect of the process on the powder to determine the level of aging, understand how many cycles we can recycle our powder, and what is the ideal mixing ratio that enable to have a stable process and consistent part properties. And as I said, additive manufacturing is still a relatively new technology, and people have really started to pay more attention to feedstock characterization only a few years ago. So there are still some challenges ahead to improve the way we characterize those powder and to further develop our knowledge with regards to the correlation between powder properties and process performance, especially in relationship to powder flowability. And actually, most of the techniques available, as we have seen in the presentation, evaluate powder flowability at room temperature, but powders are generally processed at higher temperature, close to the material melting point. And this can span from something just above 100 degrees up to 300 degrees for high performance materials such as PEEK, for example, which is a material that is also available for additive manufacturing. So it will be really important to be able to characterize the powders at a temperature as close as possible to the real processing condition. Also, something that is really challenging to measure at the moment is to what extent the material will be prone to generate electrostatic charges in the process. So we know also from our own experience that electrostatic charges could be one of the most common issues for build crashes in the machine. So that's a really important challenge that needs to be addressed. Also, something else that is also being highlighted by the standardization bodies such ASTM, alongside the development of specific standard for the evaluation of the relevant powder properties for additive manufacturing, is the fact that there is a clear gap in terms of instruments and methodology that can clearly quantify the powder spreadability and ideally the quality of the part bed. And ideally it would be really great if this kind of things could be also integrated inside the machine in order to have an in situ real-time monitoring of the process. So that's it for me for today. I hope you found this presentation useful and that you have learned something today about polymer powder characterization for additive manufacturing. So thank you very much for listening, and I open to get any question, and I'm keen to answer some of these questions in the minutes we have left today. And if you have any further question, or if you have any additive manufacturing needs, you have my contact details here, so you can feel free to get in touch, and you also have the details of our website. So yeah, thank you very much again.
Thanks, Enrico. That was great. Really good to learn about the the properties that you're evaluating there for your applications, and the techniques that you're using as well. So as you can imagine, there's been a lot of questions raised during your presentation. I'm just scanning through these because I've got a few actually that are very similar subjects, so try and put a few together and hopefully address a few questions with one of your answers. The first one is, are you using this data, including the flow property data, to specify new materials? And if so, is this just currently for your internal use, or are you requesting this from existing and potential suppliers?
At the moment, we are mainly using some of this data internally, especially the flowability data, which, as I said, is nothing really standardized at the moment. So we really try to use this at the moment internally to define our own specification and our own metrics to determine if a powder is suitable or not. But I think from a generalist perspective, we're looking at the future of the industry and seeing the industry moving towards using the technology to serial production. I think this will be a requirement to have this kind of property really specified also from our supplier, and obviously once the standards will be available, that will definitely help to have sort of an agreement between manufacturer of materials and end user. So I think it's really important to develop those standards.
Sure, well, yeah, great. That leads nicely on to another question that we've had actually. So you touched on standards in the presentation, and one or two people have asked if you could comment on that more. Is there anything more you can say on where standards currently are?
We are involved in some of the discussion, especially with the ASTM. There is the F42 committee that is really looking more specifically to develop standard for AM. I know that there are currently, really, as I said, with regards to those gaps in terms of powder spreadability. There are some projects going on. One of them, I think, is led by the MTC here in the UK. There are other consortium also looking at qualification of material. One I can think of is the MAP, again in the UK, led by Sheffield University. So I think there is more and more interest in developing new standards for powder characterization for additive manufacturing, and both for metal and for polymers and ceramics.
Okay, great, thanks. And I guess kind of leading on from the standards question, in terms of methodologies and parameters that you're using, are there any other techniques that you use that you haven't mentioned today? Particular questions have been asked about other flow properties that you potentially measure with FT4, and also things like surface energetics.
We have done in the past some measurement with regards to the specific area of the particles, but we have really not been able to define a clear link between the properties of in the process of the powder and this kind of measurement. Something that we also find quite useful with the FT4 is the compressibility test, where you actually applying a force on the powder and you measure the compressibility percentage of the powder as a function of the applied pressure. And again, this is another test that enable us to differentiate powder, because powder, they might have different compressibility kinetics, and again, it's something that we are trying to correlate how those kinetics will link to final part properties, especially in term of porosity, which is again something that it's really important to assess, because we really want to have the part as dense as possible. So again, there's a lot of work going on that side as well. We keep learning.
Sure. Okay. And we've had a couple of questions along the lines of segregation. So do you experience segregation? How do you quantify that? And do you do anything to try and prevent it?
It's something that we are not really observed with the powder we process on a daily basis. The other thing, I think, is quite challenging to measure that in real time in the process. We have sometimes took some samples during the process, do the particle size distribution, haven't observed really any major difference. I think it's really depending on the kind of printer you're using, how the powder is stored and fed, and also the type of material. So from our perspective, we haven't experienced those kind of problem, but I think there is still more work that we can do to investigate even more.
Sure. Okay, thank you. A couple of questions relating to, you showed some information on powders that you described as powders 1 to 7 that were all similar materials with similar particle size distributions. You saw some differences in their flow properties. So one of the questions is, does that then translate to how they performed in process, even though they had similar particle size distributions? And given that there were some different values for bulk density, can you comment at all on their apparent density and how that affects the ability to compare the flow metrics?
Yeah, so in sort of some of this powder we have tested on the printer. We haven't tested them all, so it's difficult to really give a full picture on how they will perform in the real process. And some of them we have processed on a large printer. Some of them we have processed. We got a desktop SLS printer that we can use to do initial qualification of the material. So again, sometimes it's also difficult to compare different printers that have got different recoater, for example. So that's one of the challenge. So that those results give us a good indication, a good overview. But as I said, there is still work that needs to be done to try to make those correlation.
Okay, and obviously one of the things you've demonstrated in your presentation that there's a lot of things to consider when characterizing powders. So everything from the thermal properties, the properties of the particles, the bulk behavior. How are you looking at all that data as a whole? Are you using things like principal component analysis?
What we do at the moment, we use those data, as I said, from at the early stage in the project, where we want to, for example, assess and identify the difference between different powders. And it's for us, it's a knowledge base in progress. So it's really try to have as much data as we can for different powders, and as long as we then test them on the printer, it's trying to really establish a correlation with between the properties and the powders and the performance in the printer, so we can speed up then the development process using using all this learning. This is the sort of the rationale behind of doing all this kind of tests.
Sure, absolutely. So it's a very kind of pragmatic and practical process of correlating the two. Great. I mean, that again leads nicely on to another question we've had, that how are you assessing the performance of a powder in a printer? Is it simply by looking at the properties of the final part, or do you have any other ways of assessing performance at the moment?
No, at the moment it's very much assessing the properties of in the final part, and obviously when we run the first test on a printer is really looking at how the powder behaves, try to adjust the processing parameter and see what's the effect on the powder, so in terms of spreadability, in terms of the quality of the bed. So we generally start with on a small scale, as I said, on a small desktop printer, and then we progressively scale up the process with the different printer we got in house, and try to optimize the processing. But it's really very much a trial and error to fine tune the processing parameter at the moment.
Sure. Okay. I think that probably addresses one of the other questions we've had about using that data for kind of troubleshooting as a trial and error to learn I'm guessing that you learn where those properties need to be in order to get that optimized process and fine tune them within those ranges. Yep.
Yeah.
Okay.
Yeah, that's correct.
And I think we're coming close to the end of our scheduled time now, so I think maybe time for one final question. Apologies, as I say, if we haven't got to anybody else's, we will address these later. But can you comment on any work that you've undertaken so far looking at electrostatic charging and the influence that has on the process?
Yeah, at the moment we haven't really tested that on a sort of an analytical instrument. So it's really something we are really keen to investigate more. I think there are some options out there that we might want to investigate in future. But yeah, at the moment it's not something that we have really pushed that forward, to be honest. But we see that as something that is definitely something we need to look more in depth, to try to really understand the correlation between issue we sometimes have seen in the process and the powder properties.
Sure. Okay. Well, thanks for that, Enrico. That's been great. As I say, I think we're kind of up to our scheduled time now, so I think we'll draw a close to the questions. And as I say, if you have asked a question that hasn't been answered, then one of our team will get in touch with you over the coming days and try and answer that for you. Thanks again to everybody for attending. At the end of the webinar, when you leave, there will be a short survey. If you could take the time to just complete that survey, it's really appreciated as it helps us tailor future events. If you do have any questions about what you've seen today, on the screen there you can see the contact details for micromeritics.com and freemantech.co.uk, including the two email addresses, info@micromeritics.com and info@freemantech.co.uk. Likewise, if you want to contact Enrico directly about what Ricoh are doing, his email address was in the presentation, which you can access afterwards, which is enrico.gallino@ricoh-rpl.com. And with that, just like to thank you again, Enrico, for your great presentation and for your time. Thanks everybody for attending, and goodbye.
Thank you. Bye. Bye-bye.